Okay, to start with, let's take a look at the idea of a standing wave on a string. Let's say you have just a guitar string, for instance, that is fixed in place on both ends. So like both ends are attached in place and cannot move. If you've got a standing wave on a string like this, what kinds of behavior have to be happening at the endpoints if they cannot move? In terms of like what part of the standing wave would the endpoints have to be? Yeah, those are going to have to be nodes. If they could move, if they could move quite a lot, they could be antinodes. Like for instance, if the ends of the string were flexible, like let's say instead of a string that's nailed in place on both ends, let's say you have a metal bar and maybe you're holding it lightly in the middle, but the ends are free to vibrate. In that case, we would expect the ends to be antinodes because they're able to move. But if the ends are fixed in place, then they've got to be nodes. That is, locations that are always destructive interference. So the end points here are going to be nodes. But you could have, for instance, an antinode in the middle. So maybe your standing wave looks kind of like this. And this diagram essentially means the highest and lowest the string can go. So for instance, at this location, the string goes up to here and down to here as it vibrates. At this location, the string goes up to here and down to here as it vibrates. And at this location, it's not moving at all. So that's basically like if you imagine the string is moving, and let's say you take a video of this with a video camera, but it's moving so fast that it looks like it's blurry. Then this would be the blur of the string as it vibrates, the highest and lowest it goes. And yeah, we would call this the n equals 1 case. And n doesn't have to always mean the number of antinodes. It kind of depends on which type of wave we're looking at. I usually think of n, in the case of the fixed, or open, I usually think of like if both ends have to be nodes or if both ends have to be antinodes, that kind of standing wave. I usually think of n as representing how many half waves we have. In the sense of like a complete wave would be like from equilibrium to a crest to equilibrium to a trough to equilibrium. That would be what I consider a complete cycle, a complete wave. But in this one, we only have half of that. In this particular case, if you have a wave that's fixed on, that's got nodes on both ends, then n is the number of antinodes. But for other types of standing waves, like for instance, if you have antinodes on both ends, in that case, if you have antinodes on both ends, your n equals 1 wave would look like this. You'd have antinodes on both ends and a node in the middle. So in that case, n would be the number of nodes rather than the number of antinodes. But this still counts as half of a wave because, for instance, one full wave would be from crest to trough to crest again. But the n equals 1 case is a single half wavelength. So I think that's probably the most effective way to think of n in these cases. N represents the number of half cycles. For instance, if we take a look at the n equals 2 case, let's say we have the same string, and we still have nodes on the ends. But you can make this one step more complicated by adding another node in between. And then, of course, you'd have equally spaced antinodes in between those. So that's going to look something like this. Again, with these curves representing the highest and lowest each piece of the string can go. Or you might think of it as like the blur you would see if you tried to take a video of this. But again, if you look at this in terms of half wavelengths, each one of these sort of humps is a half wavelength. Here's a half wavelength. Here's another half wavelength. There's 2 copies of a half wavelength, so this would be the n equals 2 case. And we usually call those the first harmonic and the second harmonic, and then the third harmonic, fourth harmonic, and so on. First harmonic is also known as the fundamental vibration. Or fundamental mode. And then n equals 2 would be the second harmonic. Yeah, fundamental frequency just means the frequency of that fundamental harmonic. And these terms show up in music theory too, of course, because music theory is all about these standing waves you get from the same string. If we take a look at the third harmonic, for instance, what would be the next more complicated thing we could do here? If we still have to have nodes on the endpoints, how else could we make this just a little bit more complicated? Yeah, instead of just adding one node in between, we could add two more nodes in between. And again, we still have to have antinodes equally spaced in between those. So our third harmonic is going to look something like this. In terms of the shape of those vibrations. And again, if you think of this in terms of half wavelengths, here's a half wavelength, here's another half wavelength, and another half wavelength. So that's 3 half wavelengths. So we would call this the n equals 3 case, the third harmonic. Any questions on the terminology there so far? And ultimately, the reason why half wavelengths are so important here, if you start at a node and you go exactly half a wavelength forward, you're now at another node. Half a wavelength takes you from node to node, or from antinode to antinode. That would also be half a wavelength. So if you have a whole number of half wavelengths, that takes you from a node to eventually another node, or from an antinode to another antinode. So in general, as long as the endpoints are the same type of point, both nodes or both antinodes, you have to have a whole number of half wavelengths. That is, the length of the string or pipe or whatever it is, has to be a whole number of half wavelengths in order to fit a standing wave of this type on the string. Now, if you've got a node on one end and an antinode on the other, things are going to be different. But to have nodes on both ends or to have antinodes on both ends, the length of the string has to equal a whole number of half wavelengths. If it wasn't, like let's say we take this string and make it a little longer. In that case, let's say that's only another quarter wavelength. That's not going to form a proper standing wave because we don't have nodes on both ends anymore. You got to have a whole number of half wavelengths to make this work. And we can write that as an equation. Length of the string, let's call that L. A whole number, let's call that N. And then half wavelength would be lambda over 2. So in general, L, the length of the string, has to be a whole number of half wavelengths. And N in this case ends up just being the harmonic number, which harmonic we're talking about. Any questions on that so far? Yeah, I think it's very important in cases like this to understand exactly what these variables actually mean in terms of their physical representation. I think it's very helpful to think of N as representing the number of half wavelengths in these equations, or in this type of standing wave. And then L is the length of the string or pipe, if you're talking about like a woodwind instrument, for instance, and lambda is the wavelength. And then if you solve that for lambda, what would you get? Yeah, multiply by 2 and divide by n. So that is a formula for the wavelength of the nth harmonic. For example, if we take a look at the first harmonic, the fundamental vibration, 2L over n would be 2L over 1, so that's just 2L. For the second harmonic, wavelength is 2L over 2, so that'll just be L. For the third harmonic, wavelength would be 2L over 3, so that's 2/3 times L. And in fact, if we look at those wavelengths, for the first harmonic, the wavelength is this whole thing, one full wave. That's 2 times the length of the string. For the second harmonic, one wavelength is the length of the string. For the third harmonic, one wavelength from start to finish, that's one wavelength, and that's exactly 2/3 of the length of the string. So that's the 2/3 L we have right here. And you can keep this going as far as you want. If you wanted to find the wavelength of the 7th harmonic, lambda sub 7, you just have 2 times the length of the string divided by 7, or 2/7 the length of the string. So this progression keeps going as far as you want, and it's usually called the harmonic sequence: 2L over 1, 2L over 2, 2L over 3, 2L over 4. In fact, you may have seen this in calculus. The idea of the harmonic series is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. The name harmonic here comes from this same idea, that all the harmonics are something over 1, something over 2, something over 3, something over 4. So the harmonic series is just all of those terms added together. And one of the weird things about the harmonic series is that it does not converge to a finite number. You're adding smaller and smaller pieces, but it ends up adding up to infinity because they're not getting smaller fast enough. But this is the reason why it's called the harmonic series. I had wondered about that for years. Like, does this have anything to do with music? But it's called the harmonic series because it follows the same pattern as the something over n for the harmonics of this wave on the string. Any other questions about the wave on a string so far? And one other thing you can do here, wavelength is like important for the string itself, but when you transition from one material to another, like the waves on the string create sound waves in the air, which cause vibrations in your eardrum. So that's changing from medium to medium to medium. The wavelength is going to change when it changes from a string to air to your eardrum. But what doesn't change when a sound travels from one medium to another? What stays the same? That is, what aspect of the wave does not depend on the medium it's traveling through? Yeah, the frequency or the period, whichever way you want to describe it. Same information, just different points of view. And yeah, the source in this case, I guess you would say, is the vibrating string. The string can only vibrate at certain wavelengths. Like, let's say this is a 1 meter long string. The string can have a wavelength of 2 meters, or 1 meter, or 2/3 of 2 meters, or 2/3 of a meter, I mean. So there's only certain wavelengths that will work. Wavelengths that are in between those values won't work because they don't form standing waves. But the string vibrating with one of those wavelengths will cause a sound wave with a correlating frequency. And the frequency determines the note you hear. So this string, since this string is capable of vibrating at several different wavelengths, it's going to be capable of producing several different frequencies of sound. And if you know the wavelength, how do you typically find the frequency? How are those related? Yeah, frequency is speed divided by wavelength. Yeah, from the formula V equals lambda times F, speed equals wavelength times frequency. And so divide both sides by wavelength, you get frequency equals speed divided by wavelength. V here would just be the speed that the wave travels in the string itself. Because the sound wave is being produced in the string, so we should be using speed of the wave in the string. If we fill that in, like let's say we know the speed of the wave in the string, and then replace lambda with 2L over n, we're dividing by a fraction, so we can just multiply by the reciprocal. And we now have a formula for the frequency of the nth harmonic. So for instance, if we fill in F1, the fundamental frequency, V times 1 over 2L. Or if you plug in 2 for n, F2 would be V over 2L times 2. Or the third harmonic would be V over 2L times 3. fourth harmonic, V over 2L times 4, and so on. In general, the nth harmonic is going to be V over 2L, which is the first harmonic, times n. We could even write this as 2 times F1, 3 times F1, 4 times F1, and so on. In general, the nth harmonic is going to have a frequency of n times F1. N is, n acts as a scalar multiplier. I mean, when we write Fn here, this should really be F sub n, I should write. So like as a subscript. So the first harmonic, the fundamental vibration, has a fundamental frequency of speed over 2 times the length of the string. And you can control that. When you're designing a musical instrument, you get to choose the length of the string from the bridge to the peg. And you can also determine the speed. How would you determine the speed of the wave on the string? What properties of the string do you think are going to make a difference there? Or to put it another way, what do you adjust in order to tune a stringed instrument? Like if you have a guitar or a violin and you want to tune it, how do you adjust the note it's producing? Yeah, you stretch or loosen the string. And ultimately what that does, you're not changing the length because the length is still from the peg to the bridge, but you're adjusting how tightly stretched it is. You're adjusting the force of tension in the string, and that modifies the speed. It turns out that the speed of the wave in a string equals the square root of tension over density. That is, the tighter the string is stretched, the faster the wave travels. The heavier the string is in terms of kilograms per meter, the slower the wave travels. So you can adjust the speed of the wave, the value of V in this equation, based on how tightly stretched the string is and how dense the string is. Density is more of a matter of design of the instrument in the first place, what material the string is made of and how thick it is, which is why stringed instruments tend to have several different thicknesses of string for easier tuning. But the tension you can adjust on the fly by changing the tension, turning the tuning peg. So typically you tune an instrument, a stringed instrument, by turning the tuning peg to adjust the tension, which changes the value of V. Higher speed means a higher pitch. Slower speed means a lower pitch. And of course, the length of the string you don't really change when you're tuning, but when you fret, when you put your finger down on a string to pinch it off, you're making the string that much shorter because only the part that you're not pinching can vibrate. So you change the notes while you're playing by pushing on the string to pinch off part of it, so only this much of it can vibrate. That changes the effective length. You can also tune it by changing the effective speed by changing the tension. And both of those go into what note it actually produces. Any questions on that so far? And if we take a look at a little bit more music theory here, if we take a look at the changes here from fundamental frequency to second harmonic to third harmonic to fourth harmonic, if you're transitioning from, let's say, first harmonic to second harmonic, what's the change associated with that? If you're changing from F1 to 2 times F1, what's the change there? What have you just multiplied by? Yeah, that's a times 2 multiplier. So if you're changing from the lowest note the string can produce, F1, the fundamental frequency, to the next lowest, you're multiplying the frequency by 2, you're doubling it. Anyone happen to know what change in pitch that corresponds to? What happens to what you actually hear if you have doubled the frequency? That is, if you're listening to some note and then you double the frequency, what happens to the note you hear? What difference would you notice? It's going to be a higher pitch, yeah. And doubling the frequency specifically is much more precise than that. that it's not just any higher pitch, it is specifically up 1 octave. That if you double the frequency, you're increasing the pitch by exactly 1 octave. You're going from, like, let's say a G note to the next G note up the scale. So doubling the pitch increases by exactly 1 octave. Or if you go from F2 to F3, what's the multiplier that takes you from 2 to 3? That is, if you're starting at 2F1, what do you have to multiply by? Yeah, you got to multiply by 1.5. So multiplying by 1.5 also is raising the pitch, not by a full octave because you're not doubling it. It's sort of a half octave. It's specifically, I think it would be a major fifth, like from a G to the next D. So instead of da, da, it's da, 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 da. Don't quite have the pitch right there, but that's up a major fifth. So a specific interval of note. But if we go from 2 to 4, what's the multiplier there? Yeah, that's another times 2. So that's another octave. So from F1 to F2, you're going up 1 full octave. From F2 all the way to F4, you're going up another full octave. But from 2 to 3, there's another in-between note. So this one string can produce a note, the same note 1 octave up, the same note 1 more octave up, but also an in-between note that sounds good with the other ones. And this is ultimately the foundation of chords. Certain combinations of notes sound good together because they can all be produced by this same string. And realistically, when you pluck a string on a guitar or a violin or a harp or whatever, you're not specifically telling it to vibrate with a certain frequency. You're just creating a chaotic jumble of vibrations that's all frequencies at once. But the only ones that persist, the only ones that you continue to hear after a fraction of a second, are the ones that fit these nice, neat patterns. And so certain notes sound good together because they're all being produced by this same string. In fact, if you pluck a string that creates some of these notes, you might notice that some of the other strings on the string instruments also start to vibrate a little bit. They're vibrating in resonance because they also match these frequencies. In fact, if you just like shout at a stringed instrument at the right note, at the right pitch, some of the strings will start to vibrate with the shout because they match the same frequency. That frequency is able to create a standing wave. Any questions on the music theory behind this, or the physics behind the music theory so far? Yeah, I always like to see how all this actually applies to music, because music at the very foundation is all about standing wave. And of course, how you actually put those together and the emotional feelings that produces. And there's a lot of psychology and culture involved in that as well. But at the very bare bones foundation, it's all about the physics of standing waves. Let's take a look at how this same principle applies to quantum mechanics as well, because quantum mechanics at the foundation is also all about standing waves. It's just that instead of standing waves of like strings vibrating and creating sounds, it's these standing waves of the electrons themselves. One of the biggest foundational concepts in quantum mechanics is that we're going to be treating the electron itself as a wave. And we usually think of electrons as particles, like a tiny ping pong ball with a negative sign drawn on it that's moving around. But it turns out that the electron in some ways acts like a particle and in some ways acts like a wave. And this means if you have the electron confined to a small region of space, such as the interior of an atom, then that's a wave confined to a region of space, and that means it acts like a standing wave. To start with, let's assume that the electron is in a narrow one-dimensional box. Like if you imagine just a narrow pipe, a box that's one-dimensional instead of three-dimensional. Let's say you've got this box that the electron's in, and let me make several copies of that same box. If you think of the electron as a particle, then we would typically visualize that particle just moving around within the box and hitting the wall and bouncing off and moving around, bouncing from wall to wall. But it turns out that an electron doesn't actually act like that at all. In this confined space, the electron acts much more like a wave. And that is a wave in a confined space, so it's going to be a standing wave. And what sorts of points would you expect the endpoints to be here if it confines to be within this box and cannot leave? Yeah, these act like closed ends. And ultimately, the reason for this, anytime you're dealing with a wave, usually the first question should be, what's vibrating? Because a wave is all about vibration. And for the quantum wave of the electron itself, or any subatomic particle treated as a wave, essentially what's vibrating is probability, the probability of there being a particle there. If we say the endpoints are nodes, we're saying there is essentially zero probability of the particle being there. Because we know the particle is not going to be outside the box. So we should expect the probability of being outside the box is zero. The probability of being inside the box is going to be greater than zero. But we got to have continuity. So at the endpoints, it's still zero. But in between, it can be larger than zero. The simplest wave would be the n=1 case, which ends up looking just like what we had before. Nodes on the ends, antinode in the middle. Then for the n=2 case, we still need to have zero probability at the endpoints. But we could also make things more complex by having a single node in between. So that'll look something like this again. Exact same sort of pattern. Any questions on that so far? And usually we can call that the n=1 and n=2 cases. And ultimately what this means is that like the antinodes are locations where it is very likely to find the electron. Like in a case like this, I would expect it's very likely for the electron to be in this region or this region. So if you take a lot of experimental measurements, you're going to find the electron, like if each of these dots represents a location where you find the electron, you're going to find the electron very frequently in these in-between zones and very rarely anywhere else, and presumably never in the location with the node. Because a node means a 0% chance of the electron being there. An antinode means high percent chance of the electron being there. And we could keep this going. We could draw out the n=3 case, which is going to have the same sort of pattern, nodes on the ends, two antinodes in between, and this sort of shape. Exact same pattern. It's just that now instead of the wave representing motion of the string, the wave represents oscillation in probability of there being an electron there at all. And of course, the electron is going to be somewhere. It's just that we have varying probability of where it could be. So if this is the same sort of pattern, what equation can we still use here? What results from earlier are still valid?
Is it lambda equals 2L/n?
Yeah, we can still use that. The formula we got for wavelength, that was just reliant on the idea that the length of the string, or in this case, the length of the box, has to be a whole number of half wavelengths. That's still true. We still have to have a whole number of half wavelengths as the length of the box, because otherwise it wouldn't start and end at a node. So we can still rely on this fact. It is true for the frequency of the electron, but usually we don't really care about the frequency of the electron because it's not like we're listening to the electron. And wavelength ends up being a more useful measurement here. If we did want to know the frequency of the electron, we could certainly still use this. But frequency of the electron turns out to be not as useful as wavelength. So typically we just leave it as wavelength. But good question. If we did care about the frequency of the electron, we could certainly use this same formula. And we might even talk about octaves of electrons. But it turns out that frequency is not as useful a measurement. What we can do though, instead of converting wavelength to frequency, we can convert wavelength into energy. Specifically, one more step in between. Let me clear this for a moment. One more step in between. Have you seen the idea of the de Broglie equation and the idea of de Broglie momentum or effective momentum? What's that idea? What's that talking about? Equation. Yeah, the idea that wavelength and momentum are related. And I mentioned earlier, we usually think of electrons as being particles, but they also behave like waves. Yeah, formally a wave is anything that has wavelength. A particle is anything that has momentum. But since the electron acts like both a wave and a particle, it has wavelength and momentum. And they're related by the de Broglie equation. Wavelength times momentum equals Planck's constant. H being Planck's constant, which is a very small value, is something times 10 to the negative 34, I think. Yeah, 6.63 times 10 to the negative 34. And I think that's joules times seconds to get the units to work out right. So an extremely small, essentially a conversion factor to convert between wavelength and momentum. So if you have the wavelength, you can now solve for the momentum. And this ends up being very similar to if you know the wavelength, you can solve for the frequency. It's just that we're using momentum and Planck's constant instead of frequency and speed. But if we now solve this for wavelength, h over p, we can replace lambda with 2L over n. Or I guess we should do this the other way. We want to know the momentum. We have wavelength. We're trying to find momentum. So Planck's constant divided by wavelength. And since we're dividing by a fraction, we can just multiply by the reciprocal. So h times n divided by 2 times the length of the box. So that tells us the momentum. And note that this only comes in certain discrete values. N can only be whole numbers. The in-between values don't form standing waves, which means there's a certain fundamental momentum. P sub 1 would be h over 2L. That would be the smallest momentum the electron can have. And then the next smallest, P sub 2, would be 2 times h over 2L. And then the next smallest would be 3 times h over 2L. In other words, 2 times the fundamental momentum, 3 times the fundamental momentum, and so on. So there's only certain discrete values of momentum that can exist here. And this is somewhat weird in terms of our expectations of everyday objects, because typically if you've got like a rock, you could throw that rock with a certain amount of momentum. You could throw that rock with a little more momentum, or a tiny bit more momentum, or a lot more momentum. There aren't really restrictions on the momentum that rock can have. But for the electron, it can have this much momentum, and it can't have less than that. It cannot have 0 momentum. This electron cannot be at rest. And then it can have this much momentum, exactly twice as much, but in between values do not work because they don't form standing waves. So you can only have this much momentum or a whole number of multiples of that much momentum. And this tends to be very common at the very small level. If you're talking about like individual atoms or individual electrons, they tend to form these standing wave patterns, and that means only certain values of momentum will work because the in-between values don't form standing waves. Now, if the electron is not confined, if it's free to move, it can have any momentum at all. But if it's trapped in this container here, if it's in a restricted environment, then it has to form a standing wave. So it can only have these certain values. Any questions on that quantized momentum so far? Quantized just means it can only have certain values and no one in between. Also, momentum has to do with motion. We can also talk about energy here. What type of energy is associated with motion? Yeah, kinetic energy. We can convert each of these momentum formulas into a kinetic energy formula. The strings, you mean like the strings with the standing waves? The strings also only came in certain specific whole number values. Like if you take a look at those frequencies, the frequency of the second harmonic was exactly twice as much as the first harmonic. The third harmonic was exactly 3 times as much as the fundamental frequency. The fourth one was exactly 4 times as much as the fundamental frequency. And you can certainly get fractions if you're looking at the higher values compared to each other. But you can do the same thing here. Like if you compare, for example, the second momentum and the third momentum. The third momentum is exactly 1.5 times as much as the second momentum. But they're all exact whole number multiples of the fundamental momentum, P1. Yeah, you're welcome. So in fact, this is following exactly the same pattern. The idea that the nth momentum is exactly n times as much as the fundamental momentum. Exactly in the same way that for the waves on a string, the nth harmonic had a frequency that was exactly n times as much as the fundamental harmonic. So it is following the same pattern in terms of n times some constant that is the fundamental harmonic. So if we want to convert this to kinetic energy, though, because if we're talking conservation of energy, then it's important to convert the momentum into the energy. And to do that, we can take a look at the usual formula for kinetic energy. Classically, what's our usual formula for kinetic energy that we've been using all along? Yeah, 1/2 mv squared. However, since we don't have a formula for speed of the electron, but we do have a formula for momentum. And what we want to do is we want to relate kinetic energy to momentum. Classically, we also think of momentum as being mass times velocity. In quantum mechanics, we don't really look at momentum as mass times velocity. We look at momentum as more of a fundamental property the particle has, and we don't really care much about velocity. But if we want to relate these together, can you combine these to get an equation for kinetic energy in terms of momentum that doesn't care about speed at all? Is there any way you can modify one of these formulas to make it look like part of the other? Yeah, if we modified P, yeah, for example, if we solve this for V, that would just be P over M, momentum over mass. And we can substitute that into the other equation. That would become kinetic energy equals 1/2. I'm just going to write that as, yeah, 1/2 times M times P over M squared would be P squared over M squared. And if you simplify that, what do you get? What's going to happen when we reduce this? We don't need a square root here because we already have kinetic energy isolated by itself. But notice that we have M in the numerator and in the denominator. So what's going to happen when we reduce that? Yeah, one of the m's cancels out. We're left with just one m in the denominator. Since this m cancels out one of these. And the 2 is also in the denominator. So if we just combine that into one big fraction, we get momentum squared in the numerator divided by 2m in the denominator. And it turns out that this is usually used as effectively the formula for kinetic energy in quantum mechanics. In quantum mechanics, we usually just treat this as the definition of kinetic energy. And it works out to be the same thing as kinetic energy in the classical approach. If you replace P with mv, you just get back to 1/2 mv squared again. But this turns out to be a much more useful way of defining kinetic energy in quantum mechanics because it relies on momentum instead of velocity. And we have a formula directly relating momentum to wavelength. Probability is ultimately going back to the idea of these graphs of the standing waves. You can think of the standing wave as a graph of probability, that nodes are locations where probability is 0, and antinodes are locations where probability is very high. So if you have a diagram of the standing wave, then any locations, for instance, in the n=3 case, the nodes would be locations where there's effectively no probability, zero probability of finding the particle. So at those four locations, those four nodes, you would not ever find the particle at those locations. You would be most likely to find the particle at the antinodes. So it's going to be very likely to find the particle at these three locations, and fairly likely to find the particle near those three locations, but very unlikely to find the particle near the node, and impossible to find the particle at a node. So the standing wave here literally is just a graph of probability. I think it's really more like that value squared is the probability, but you can think of the height of the wave, the amplitude of the wave, as acting like probability there. Formally, again, I think it's amplitude squared is probability, but similar idea. But going back to this formula for kinetic energy, momentum is very useful here because we have a formula relating momentum to wavelength, specifically the de Broglie equation. So that ties these together. In fact, by using the fact that momentum is specifically h times n over 2L, we can combine these equations. That we know that kinetic energy is momentum squared divided by 2 times the mass, and we have a formula for momentum. So we can combine those by just taking that formula and plugging it in for momentum here. Of course, we're going to have to square it. So this whole thing gets squared, h squared, n squared, 2 squared, and L squared. But putting those together, then we get kinetic energy equals that whole thing squared. So h squared times n squared divided by 2 squared L squared. So that's 4L squared. And then we're also dividing by 2m. So we get a times 2m in the denominator also. So this piece, is momentum squared. And then we're also dividing by 2m, so we need a 2m in the denominator as well. Any questions on the algebra there so far, the substitution? Yeah, because if we multiply those, we've got a 4 times 2, so those combine to 8. And we've also got an m and an L squared. So we can simplify this to, in the numerator, h squared, that is Planck's constant squared times n squared. And in the denominator, 8 times m times L squared. That is 8 times the mass of the particle, the electron's mass, times L, the size of the box, squared. So that's our formula for kinetic energy of the electron. And since it relies on n, we usually call it Ke sub n. But that means kinetic energy itself is quantized. Kinetic energy doesn't come in any value you want. It only comes in certain discrete values. N can be 1, n can be 2, n can be 3, n can only be whole number values here. Yeah, if you increase n, the energy increases. But it's not just proportional. Like if you switch to, let's say, the fourth state, the n=4 state, you don't get 4 times as much energy because what's being done to n in this equation?
You're squaring it.
Yeah, n is being squared. So let's say we're looking at the fourth harmonic, n=4. If you plug in 4 for n, but then you square it, what do you get?
16.
Right, so that means the fourth state, the n=4, the fourth harmonic you might call it, is going to be 16 times as much energy as the fundamental state, the base energy. So it's going to be increasing energy proportional not just to n, but proportional to n squared. And a very useful way of drawing that diagram, let me clear some space here, get rid of these standing waves. Since what we most care about is the energy, what we often do is draw out essentially an energy axis, like almost like a graph of energy versus something, except we don't have another something we care about. It's just an energy axis. So let's say this axis represents energy. And we're just going to draw out roughly to scale all of the energies this value could have. What's the lowest value n can be? Yeah, if you plug in 1 for n, you get a lowest possible energy. And notice that that energy is not 0. It's actually impossible for this electron to have 0 energy because n cannot be 0. That would not form a standing wave. So a little above the bottom of this graph, I'm going to draw a bar representing the lowest possible energy. So that energy is n equals 1. And let's call that Ke sub 1, which is h squared over 8 ml squared. That's the lowest energy this can have. The next energy it can have, what happens if we plug in 2 for n? What does the overall energy get multiplied by? It's not just going to be 2 though, because remember n is being squared. Yeah, we're going to get 4 times h squared over 8 ml squared. But since h squared over 8 ml squared is just Ke1, we can abbreviate this by just saying 4 times Ke1. In other words, it should be exactly 4 times as high as the base energy. So this is going to be 4 times as high. Make that a little more scale. 1, 2, 3, 4. So maybe something like that. And then what about Ke3? How do we write that out in terms of Ke1? How many times higher would it be? Yeah, you plug in 3, you get 9 from 3 squared. 9 times h squared over 8 ml squared. So 9 times h squared over 8 ml squared, or to abbreviate that, 9 times Ke1. So that's going to be 9 times as high as the original. And notice that that's a larger gap. Going from 1 to 4, you'd have to add 3. Going from 4 to 9, you'd have to add 5. So this is a bigger gap. It takes more energy to get from 2 to 3 than it did to get from 1 to 2 because of the n squared in the formula. Or what if we plug in 4 for k, or for n, I mean? That's going to be, we already saw that was what, 16 times as much? And that represents an even bigger gap. So that's going to be like somewhere up here. And then the next one, Ke5, will be 25 times as high. So even off the chart we've got so far. But the important thing about this is we still have to follow conservation of energy. If you have a particle in one state, like let's say you're currently in state 2. Let's say your electron is currently has exactly enough energy to be in state 2. If you wanted to bump that up to state 3, what would you have to do? Yeah, this is exactly where these energy diagrams come from. If you see a diagram like this with a bunch of bars representing energy levels, the energy levels come from some sort of formula like this. And there's different formulas, of course. This formula, the h squared n squared over 8 ml squared, this only applies specifically to the idea of an electron in a one-dimensional box, or any particle in a one-dimensional box. Other situations like an electron in an atom or 2 atoms oscillating are going to have different formulas, but there's still going to be formulas that lead to certain values working and other in-between values not working. So we can still graph it out like this. It'll just have different patterns of how far apart the energy levels are. But in general, if you want it to go up to the next level, what do you have to do to it? Would you have to add energy or remove energy, or is it just going to happen on its own? It's not so much a multiplication thing here, though. You can't just like say, let's double the energy. You'd have to provide that energy. And to add energy to it, typically to add energy to a quantum system, you do so by shining light on it. Light, you send in these photons of light. Yeah, exactly. You shine light on it. A photon of light hits the system, and the energy the photon was carrying becomes energy of the system, raising it to the next energy level. Or possibly up, maybe you can skip an energy level. As long as you start at some allowed energy level and end at another allowed energy level, then you can figure out what's the difference, how much extra energy is needed to make that happen. As long as the photon of light has that much energy, then that means the quantum system can absorb that photon and gain the energy it had. Or alternatively, maybe you could lose energy. If you start off in a high energy state, you can lose energy and drop to a lower energy state. Look at the difference between these. So for instance, if you look at final minus initial, 1 KE1 minus 4 KE1 would be negative 3 KE1. So the energy loss, delta E, would be negative 3 times h squared over 8 ml squared. So you can use a diagram like this to rapidly figure out, as long as it's clearly labeled of each energy level, you can quickly calculate how much energy has to be added to jump up to a higher energy level, or how much energy has to be lost to drop down to a lower energy level. And that energy gained or energy lost has to match the energy of the photon that's absorbed or emitted. So a chart like this can be very useful. In general, anytime you've got a formula for energy at the nth energy state, I would usually start by calculating the first few values and drawing it out as a chart. Then it becomes much easier to just say, we're starting at this energy level, we want to raise it to this energy level, so we have to add this much energy. It's a much more visual way of examining the idea. And again, other types of situations are going to involve different formulas, but whatever the formula is, you can draw out a chart like this by calculating the first few levels and drawing them out to scale with each other. Any other questions on the quantum energy level stuff? All right, then we can look at more examples later. Feel free to email me or send me examples in the Discord if you have some other ideas you'd like to discuss next time, and I will see you then. You're welcome.